Let's take a look at variable length subnet masking, or VLSM, and classless interdomain routing, or CIDR, as well as some classful IP version for subnetting. So in this first problem, there's two important parts. The first octet, which gives us the class, and the CIDR. And if we look at the first octet and we know the class, we know what the normal CIDR is, then we can get an idea of how many bits we're subnetting or supernetting on. And in this case, our class of address, remember our ranges, class A would be 1 to 126, the loopback is 127. Class B would be 128 to 191, class C would be 192 to 223, and then multicast 224. So if you know that, right, if you know the class, then you also know the typical subnet mask that goes with that class. So if this is a class C address, then 3 bytes or 24 bits, 255, 255, 255 would be the normal subnet mask. However, this is CIDR 26. Well, a normal class C is CIDR 24, which would be this. So if CIDR 26 is being used, then we know that 2 more bits in the last octet or the last byte are being used for subnetting. So I've laid out a byte table here, and this is the way a 32-bit IP address would look to our computer in the memory registry. So inside the memory registry, we have each of these would be a byte composed of 8 bits, and they have powers of 2. Each place value, each column is represented in powers of 2. So by turning these bits on or off, I can hold or represent different values. And if you need to, there are other tutorials and videos previously posted where we've gone over hexadecimal and binary and base 2, base 10. So you may want to review those before watching this video. But in this first example, the normal CIDR 24, right, that 255, 255, 255 is in black here. All those bits are in black. So all that would be the network address. Now that's CIDR 24. So CIDR 26, well, that's 2 more bits. So that's how we know what we're subnetting with, those 2 bits. And in this case, what do we have? Well, there's the 128-bit and the 64-bit. And if we plug that into our formula, remember our formula is 2 to the power of x minus 2. What does that give us? 2 subnet bits, that's 2 to the power of 2 minus 2. Well, 4 minus 2 gives us 2 subnets. And then that leaves us these remaining bits here, these 6 in the last octet for our hosts. And if that's the case, 2 to the power of 6 will give us 64, minus the 2 gives us 62 hosts. So using our formula and our byte table, there's always going to be these 5 basic combinations here, okay? Anything here is, you can't have all your subnet bits on or off unless you start, bending or breaking the rules. And down here, you can't have all your host bits on or off because that will either be the network address or the broadcast. So you're kind of stuck with these 5 values in between are sort of your only 5 values. And they're based on different block values. So notice the first option, if I have 2 bits for subnetting, which is what we have here, that leaves 6 remaining for hosts. So that's 2 subnets and 62 hosts. The next available range here would be what? In this case, the 32 block value, or the 32-bit. So if I'm using 3 bits, 2 to the power of 3 minus 2, that gives me 6 subnets. And then I would only have 5 left for hosts, and that would give me 30. And then we meet in the middle. If I use 4 bits for the subnetting, that also leaves me 4 for the hosts. So I have the same number of subnets and hosts in the middle there. And then finally, it just inverts, okay? Whereas up here we had 6 subnets and 30 hosts, down here we have 30 subnets and 6 hosts, because we're using 5 bits for the subnetting, which only leaves us 3 bits for the hosts. And finally down here we have 62 subnets, but they can only have 2 hosts each. And you might be saying, why on earth would I want a subnet that only holds 2 hosts? But think about it. If you're simply connecting router interfaces or router endpoints to connect one network to another with different routers, then that's actually a good choice of a subnet, because you're not going to waste any IPs there. You only need 2 IP addresses to connect those 2 interfaces or 2 routers across a subnet or network. So those 5 basic combinations, notice the inverse relationship. You can just memorize this. You can work it out with the formula if you want, but it's probably quicker and easier if you just memorize it, kind of like you did the multiplication tables when you were in elementary school. And also each of these has a block value, right? Because of how many bits are being used, the block's always the lowest bit. So in the first example, if I'm using 2 subnet bits, my block is 64. And then in this example, it would be 32. And then in this example, it would be 16. And then in this example, it would be 8. And then finally in this example, it would be 4. Based on how many of these bits here belong to the subnetting part. That's my lowest bit. So again, you'll eventually want to memorize these combinations here and the block values that go with them, the number of subnets and hosts and things that you get. But you can always use the formula to work it out should you forget or if you just don't want to do that. And use your byte table. You don't have to do this. Once you do 10 or 15 of these, you won't really need to use a byte table, but I recommend going through and just making and using a byte table just to see mathematically the mechanics. How does it work going back and forth, binary to base 10, base 10 to binary or hexadecimal. I think it really helps you see the ebb and flow of things and how things are really addressed on memory and how they work. So let's go ahead and get into this first example. So we know, because it's normally CIDR 24, but the CIDR 26 is 2 more bits, we know that we have these 2 bits here, right? And we know that in this case, we're going to be using a block value of 64. That's our lowest bit. And our mask would likewise be, well, if we subtracted that from 256, that would give us 192. Okay? And we could also simply add these 2 up here, 128 and 64, the 2 bits that we're using for subnetting, would also give us 192. So we know how we've got the number of subnets possible, the number of hosts possible using our formula and these combinations. Of course, the number of bits for subnetting and the number of bits for hosts we figured out because of the CIDR and the class of the IP address. Subnet mask, as we just said, we figured out we could add these 2 bits together and get it. Or we could take the lowest bit, the block value, subtract it from 256. Either way, your preference. And the block value, and that's important because that's what you're going to base your networks on. The block is basically the base multiple that you'll base each additional subnet on when you're subnetting. So we know all these things, now we're ready to determine the range. And let's do that. And based on the block value, we know that the first network is going to be 64, and the next network is going to be 128. And let's look at that. Well, the first network, we would turn the 64-bit on, and the 128-bit would be turned off. The next network, the 128-bit would be turned on, and the 64-bit will be turned off. And so those are our networks. I'll try to get all this on the screen at once. Okay, so what about our broadcast address? If we use the byte table, our broadcast address is 127, which you could look at it and say, well, it's just 1 less than the next network. But again, look how it works in the byte table. The broadcast address would be all the host bits turned on. Well, these 6 bits here marked under red are the host bits. And if I turn them all on, what do I get? 32 plus 16 plus 8 plus 4 plus 2 plus 1, and then plus the 64, well, that gives me the 127. So that's where I get my broadcast from. If that's the case, what is the first valid IP address? Well, I can't... let me turn all these bits off here. Okay, so in our 64 subnet, this would be the network address, but that's not a valid IP address, right? Remember the rules? The rules are you can't have all the bits off or all the bits on for it to be a valid IP address in the host portion. So if that's my 64 subnet, my 64 network, then the lowest valid IP I can come up with is going to be if I flip this 1 bit on over here. And so the 64 and the 1 would be 65. And again, there's my valid starting IP, 65. Now what's my last valid end IP? Well, again, you could say, well, this is in the same way that this is 1 more than the network, this is just 1 less than the broadcast. But look at how it works in the byte table as well. So if I were to turn all of my addresses on, I could turn all these bits on, but in order for it not to be a broadcast, in order for it to be a valid IP, the last valid IP before I get to the broadcast, I'd have to turn at least the lowest bit, which is the 1 bit, off. And if I did that, notice that it's 126. And you'll notice that these are always odd and even. Okay? So if this case, you'll see that pattern, or you recognize that pattern or relationship. And again, you could say, well, I'm just going to subtract 1, then the next network, that's my broadcast, or I'm going to add 1 to the network, and that's my first valid, or I'm going to subtract 1 from the broadcasting. I mean, there's all kinds of numerical patterns and relationships there when you're determining the range. But the most important thing you want to focus on is how does it work in the byte table? How does it look when I flip the bits on and off? And I think, at least with me, when I was kind of first learning this, that really helped me to kind of understand how things work. I wanted to be able to think like the computer and understand how the memory was addressed and how it worked and everything with a subnetting address. So that's our first problem, and then of course, again, our second subnet would be flipping the 128-bit on and the 64-bit off. So let's move on to our next problem. Here's our next problem, and again, the two important parts of it are going to be the first octet, which will give us the class, and the CIDR notation. Using the first octet, I know that that's within the range of 1 to 126, so it's class A. And we know that our normal class A is 255, 1 byte or 8 bits, and then the remaining 3 bytes or 24 bits are reserved for hosts. However, the CIDR is 30. Well, normal CIDR would only be CIDR 8 for a class A. So again, that tells us how many bits we're subnetting with. So minus those 8 bits, there's 22 bits that are being applied to subnetting here. So I took the byte table and I just kind of colored them out. In this case, these 8 bits here are all the network part. It's the very first normal class A octet that would be used for the network address. Then the remaining 22 bits, the 8 here, and the 8 here, and the 6 over here, those are all the subnetting bits. And that doesn't leave many. That only leaves us 2 bits for hosts. So it's a bit odd, but we can still work it out using our formula. Now these ranges, because of this is an interesting situation. It's class A, and we're subnetting with so many bits. We're not really applying these 5 basic ranges here, but we can still figure out our block value. So if we use our formula 2 to the power of x minus 2, then 2 to the power of 22, right? 22 bits, because that's what we have that's more than our normal 8 bits in the CIDR notation for class A. That's going to give us, minus the 2, 4,194,302 subnets. And there are 2 host bits, and that's just going to give us 2 hosts per subnet. So we have a lot of subnets that we could use to connect routers with. Not sure about the practical usefulness of this, but it's a good example to kind of look at the formula and the byte table and the bits and how they work. So that being said, this is the important information here where I'm moving my mouse cursor around. This is the important information that you want to know and jot down or have figured out before you start working on the range or computing a valid range. So I know the number of subnets possible now. I know the number of hosts possible per subnet. Of course, now we know that because of the CIDR, the bits being used. And the subnet mask, well, what would that be? Well, 255, 255, 255, right? All the bits, all the bits, all the bits, and the first 3 bytes are octets. And this last byte, the last octet, well, we're using 6 bits. And if I'm using 6 bits, add them all up. 128 plus 64 plus 32 plus 16 plus 8 plus 4 is 252. And that's how I get my subnet mask. And my block value, my lowest bit is what? It's 4, right? The very last bit there. And so there's my block value of 4. If I know all that, okay, now I have what I need to figure out the range. So I can immediately go ahead and populate it with my networks. And based on this, just using the first octet as a network, then my networks would go like so. I build them on 4, 8, 12, let me scroll down here, 16, and 20. And then, well, okay, what would my broadcast be? Well, my broadcast would be 7, 11, 15, 19, and 23. And how so? Well, I only have 2 hosts per subnet, right? And so these octets will be turned off, and this throws some people off when they look at Class A and Class B. Because when you're used to subnetting Class C, you look at a 0 and you're like, well, that can't be a valid network address, or even a broadcast, because that's all the bits off. No, that's got to be a network or something. But remember, you have extra octets when you're dealing with Class A and Class B, and depending on whether you're supernetting or subnetting, yeah, 0 can be a valid IP. So 90.0.0.5 is perfectly valid, and we'll take a look at why in a moment in the byte table. But if you were to look at the relationship here, what, 4, well, the next network is 8, subtract 1, that gives you the broadcast, right? Same thing, the next network is 12, subtract 1, that gives me the broadcast. So there's that relationship that will give you the network and the broadcast all the way down, not even using the byte table, you don't have to. So if that's the case, I add 1, there's my first valid start IP. If I add 1 to the network, I subtract 1 from the broadcast, there's my last valid start IP. Does it match? Right, well, I only have 2 hosts per subnet. Yeah, that matches up, 5 and 6. Okay, so you could do all of that without the byte table, but again, not because we're sadistic, but just to kind of, we want to learn to understand things or think the way the computer thinks, right, in the memory registry. the way these addresses are actually processed in binary. So let's take a look at that. The network would be 90004. Well, okay, let's actually do that. So if we were going to do that, how would we turn all the bits on that would be necessary? In this case, we'd come over here and we'd turn on the 64-bit. Let me turn the 120-bit off. That would be too big, but the 64-bit, we could turn that on. We can't turn the 32-bit on because that's too large. That would be 96, and all we want is 90, right? Okay, so what about the 16-bit? Could we turn the 16-bit on? And yes, we could. That would give us 80. Okay, and then now we just need 10 more. So we could turn the 8-bit on. We can't turn the 4-bit on. We have to turn that off. We could turn the 2-bit on, and we can't turn the 1-bit on. So that in binary gives us our 90 right here, right, in the first octet, the first byte. Well, the remaining ones are easy, right? 0 and 0, the next two octets. So we're just going to 0 everything. We're going to turn all the bits off. Off, 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 off. Off, 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 off. Okay, so there's our 0 and our 0, and there's our 90. And now we get down to the last octet, the remaining 8 bits and our 32-bit address. And what are we going to do here? Well, we're going to turn these bits off, 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 off. And the very first network, based on our block, right? Remember, it has to be based on a multiple of the block. It's going to start at 4. So we would turn the 4-bit on. And if that's the case, well, if I turn the remaining 2 bits off, remember all the host bits, and these are the red bits. There's only 2 host bits. If I turn them both off, that's the network. Well, that's where we get that from, you understand? The 90004, because of the way the bits are switched on and off in the byte table. So the broadcast would be all the bits turned on. Well, there's only 2, right? Not only 2 bits. Not much to do there. So if I turn those 2 bits on, well, what's 4 plus 2 plus 1? That's 7. That's the broadcast. So neither one of those are valid IPs. The valid IPs fall in between those. They're sandwiched in between the network and the broadcast. Because remember the rules. You can't turn all your host bits off. You can't turn them all on for it to be a valid IP address. So in that example, in that case, what's the lowest address I can come up with that's a valid IP to start? Well, back when we had all these turned off, our subnet 4, the lowest combination I could come up with, if I turn this 1-bit on here, okay, well, 4 plus 1 is 5. So, and it still meets the rules because I have this bit over here, which, these 2 bits belong to host, that's turned off. So I don't have them all both turned on, so it's not a broadcast, so I'm okay there. It's good. Well, what's the next valid IP? Well, then the only other thing I can do without turning them both off or both on, and therefore breaking the rules, would be, well, I could flip this bit off, and I could turn the 2-bit on. And 4 plus 2 would be 6. Okay, so you see how that works? And that just works the same way all the way down for our ranges. Again, you've got your formula. You can use that. You've got your combinations here. You can use those when they apply. You can memorize it. You can figure it out in your head. You can draw out a byte table, and I highly recommend doing that, drawing out a byte table, maybe for your first 10, maybe even your first 15 problems, especially when you get into VLSM and CIDR and Class A and Class B, and I think it will help you really, kind of learn to think the way the computer thinks and addresses memory. So let's look at the next problem. Here's our next problem, and again, it's a Class A. How do we know? Well, we look at the first octet, and that's within the range of 1 to 126 for a Class A. And that also tells us a few other things. We know a normal mask for Class A is just 255, the first byte, and then 000. And we know the normal CIDR would just be CIDR 8. So if we see CIDR 29, we can therefore calculate how many bits we're using for subnetting. So if normally a Class A is only CIDR 8, and I see CIDR 29, and I know, in this case, I'm using 21 bits for subnetting. So let's draw that out on the byte table. And this first, byte or octet, these 8 bits here, that's just the network part. That's a normal CIDR 8. But then the remaining 21, well, these are all of our subnet bits, here all the way down to here. It's very close to the previous example. Okay, and using our formula, let's go ahead and figure the information out that we need to figure out to start working out the ranges. So 2 to the power of x minus 2, well, 2 to the power of 21 minus 2 is what? 2,097,150 subnets. And there are 3 host bits, so 2 to the power of 3 minus 2 is 8 minus 2, which gives us 6 hosts for each of those 2,097,150 subnets. So we have that figured out, right? The number of subnets possible, we know the number of hosts possible per subnet, and we know the number of bits we're using for subnetting. We know the number of bits we're using for the host because of the class and the CIDR notation up here. Now what about the subnet mask? Well, in the last octet is where we finally have host bits, once the CIDR finishes out at 29. So these 3 remaining host bits, so what does that give us for the block? Well, the lowest bit for subnetting is always the block. Even though we have 3 octets here combining for the subnet part, still the lowest bit in the last octet in this case is 8. So our block value is 8. And what's the mask? Well, 255, 255, 255, because all of these are being used for the network and the subnet. And in the last octet, if we add up just the subnet bits, these 5, not counting the 3 bits over here for host, 128 plus 64 plus 32 plus 16 plus 8 will give us 248. Or if you took the block and you subtracted it from 256, either way, whatever your preference is. But knowing this, now we have what we need to start figuring out the range. So again, if we're going to populate our range table, everything's going to be based on the block, a multiple of 8, right? So the base multiple being 8, we'd start our networks out at 8, 16, 24, 32, and 40 respectively. Now if we did that, even without using a byte table, we could look at the next network address and say, well, I know if 16 is the next network address, I know 1 minus that would be the broadcast of my previous network. So you can figure these 2 columns out pretty easily. Once you've got the basic multiple or the block, and once you realize that each of these is just going to be 1 less than the next network, you just subtract 1 going up the table. Now these, well, again, you could figure that out without the byte table. You could say, well, if that's the network, if I add 1, there's my first valid IP. And if this is the broadcast, if I subtract 1, there's my last valid IP. To check it, make sure that between 40,009 and 40,0014 are there 6 hosts. Yes, there are 6 hosts possible per subnet. That matches up. So you have 9, 10, 11, 12, 13, 14, 6 hosts. So using the information that you gathered, your formula, your combinations, you can just, you don't even really need to use a byte table there. But once again, because of the pure sadistic torture, but because we want to see how it's calculated, how it works, how it's configured, how it's processed in the memory registry, let's fill in the bits in the byte table. So for the first network, what have we got? And I'm not going to bother filling all these out because we did that in the last example, but you know what they would be. So in the last byte here, let's work this. I'll try to hopefully speed things up a little bit. So I would turn on this bit here, and then the network part of it would be, well, these are my 3 host bits, right? These last 3 bits. So everything turned off, and that's where I get my network address 8. Now what if I turned all the bits on? That's the broadcast, right? And under the red here, these 3 bits in red, those are the only host bits I have. But if I were to turn all those on, what do I get? 8 plus 4 plus 2 plus 1. What does that give me? 15. Okay, so the first valid IP would then be what? Well, if I turn these back off, the very first valid one, the lowest thing I could do is I'd have to flip the 1 bit on. Remember the rules, I can't have them all turned off, that's the network. Can't have them all turned on, that's the broadcast. So in this case, if I add 8 and 1, what do I get? 9. Everything checks out. And then the last valid IP would be what? Well, again, these are the 3 bits I'm using for hosts. They're the only ones left under the red, so if I flip them all on, that's the broadcast of 15, right? 8 plus 4 plus 2 plus 1. Well, the highest IP I can have without turning them all on would be if I flip the 1 bit off. And what do you get when you add 1 plus 4 and plus 2? And that's where you get your 14 there. So again, you can kind of see how that works on the byte table, and you can follow that through all the way down if you want. And I'm not going to do that, but I just highly recommend doing that until you kind of get maybe a few of these under your belt, so to speak. Now we have a class C. And the fourth example, rejoice! Except that this time we're not subnetting, this time we're supernetting. Supernetting, well, what is that? Well, if subnetting is robbing Peter to pay Paul, then now we're robbing Paul to pay Peter. Remember that when we subnet, we take bits from the host portion and give it to the network portion. So we lose hosts, we gain networks or subnets. When you supernet, you do the opposite. When you supernet, you take bits away from the network portion and you give it to the host portion. So you get a bigger broadcast domain when you supernet, you get a smaller broadcast domain when you subnet. And there are situations where some organizations do that. They like to supernet. So we'll look at that as an example on a Class C address. How do we know we're supernetting? Well, again, there's always two important parts of the problem. The first part being the first octet, which tells you the class under RFC standards 192 to 223 is a Class C. I know that the normal CIDR for a Class C is 24, and I know the normal mask for a Class C is 255, 255, 2550. However, the CIDR 14, if I were subnetting, that would be greater than CIDR 24. But it's not greater than, it's less than CIDR 24. So we're moving the opposite direction, and by looking at that and knowing the class, I know that, hey, I'm not subnetting, I'm supernetting. I'm moving the opposite direction. So how would that look? Well, the subnet mask will calculate that out. So if we were to apply this into our formula, and this might be a little bit odd or tricky bit, the subnet bits, well, there are no subnet bits. Remember that we're, in this example, we're gaining host, but we're losing networks. So that would just be 0 subnets there. But the number of host bits is important in the sense that where we would normally only have 8 host bits in a Class C network, now because of the CIDR 14 and this craziness, we've ended up with 18 host bits, which would give us, if we plug it into the formula, 2 to the power of 18 minus 2, 216,142 hosts. Okay, so in this case, the number of subnets possible, well, it's kind of a trick question. There are no subnets because we're not subnetting, we're supernetting. The number of bits used for subnetting, again, kind of a trick question. Well, we aren't using any bits for subnetting, we're supernetting. So 0 and 0 respectively there. But the number of bits for host is important, that's 18. And that gives us the number of hosts possible per subnet. And what about the subnet mask? How do we know that? Well, the first octet, right, there's our first 8. All of it's being used, so that's the 255. There's the no-brainer. The second octet, though, we've only got 6 bits. And after that, these 2 bits and the last 2 bytes, the last 16 bits, are all part of the hosts. So because of that, add all these up. 128 plus 64 plus 30 plus 16 plus 8 plus 4 gives you what? 252. And at the network part of it, what's our block value? Well, our lowest bit is what? It's 4 in the byte table. So there's our block value. And if we know that, again, you could also subtract that from 256, but then the remaining 2 octets here, these remaining 16 bits, it's 0 because they're all part of the hosts. So you have this, and you have this, and you have this, all part of the host there. And actually the range is pretty easy here, because we're not really, we don't really have any subnets. We're supernetting. But if you were to look at that, what would be the first valid, in this case 192, and again, we did that before, but we're just going to worry about what we've got going on in this table here. So if I had turned on the 4 here, I'll turn these guys off, then the network that I'm on would be all the host bits turned off, okay, so 192 and 4 and then 0, 0. That would be the network. So what's the first valid IP? Well, in my last octet, I could flip the 1 bit on. And so it would be 192.4.0.1. Alright? And then my broadcast would be what? I have to flip all these bits on, which means it would be I'm not going to turn all these on, but that would be 255 and 255, right? If we turned all the bits on in these last 2 bytes. And then if I add the 4 and the 2 and the 1, that's going to give me a 7 here. So it would be from my first valid IP in this case would be 192, and then 4, and then 0, and then 1, and my last valid IP would be what? 192, and then 7, and then 255, and then 254. Okay, so I could calculate all of those, but as far as multiple subnets, no. I'm not going to have multiple networks here. I'm supernetting rather than subnetting.